Hi guys, welcome to COSC100 tutorial 5, and in this video we're looking at exercise number 4. So in exercise number 4 we're going to be working with the slope and intercept functions to calculate the points on a line of best fit for a data set. So what we'll be doing is creating a regression model for a data set. So what we mean by that is we'll be able to predict one variable given the value for another for any number that we so choose. But we'll come back to that concept later on. The first chore to get this exercise started is to go and download the Iris Flowers Excel spreadsheet. And I've done that and I've got that up here over on the right hand side of my screen. So if we look at this data set, look at this spreadsheet, you can see that there's a few bits and pieces I've put in here for you. In columns A and B we have our starting data set. So these are the petal length and petal width measurements for individual iris flowers. And we can see we've got 150 observations going down to row 151. Now the first thing that we're going to do in this exercise is have a look and see what this data looks like. We want to understand if there's a relationship between the petal length and the petal width of the iris flowers that we've sampled. So we start off by dragging down and selecting all of the rows of data, and we're going to plot a scatter chart for this data. So if we go and have a look at our charts dialog, we can plot a scatter chart automatically through Excel. And so you can see straight away that it's plotted the data on a scatter chart, and each one of these points represents one of these rows or one of the observations or measurement sets from our data set. So in our situation, I want us to have our length, our petal length on the x-axis and our petal width on the y-axis. Now we can see that by inspecting the values, so you can see the y-axis, the x-axis values range from values 1 up to nearly 8. We can see that they correspond to our petal length, and our petal widths are on the y-axis here. So that's what we want to see. So provided you select the data in that order, you should see the results that I've got on the page here. So starting out, we can see straight away that there is a fairly strong relationship between the petal width and petal length of our flowers. We just want to quickly fix this chart up though, because we can see we don't have any axes labeled. So we start by jumping in to the chart layout, and we can go and put an axis title on here. So we've got our petal length. Oops. Petal length, and we've also got our petal width, so we can put one on the vertical axis as well. Petal width, oops. And we might put a more appropriate title in there. Oops, I've managed to select that. So if we go, we can edit the title of our graph. So we can go petal width versus petal length for iris flowers. Drop that in. So now we've got our graph fully labelled. We haven't put some units in there. We better go and edit that as well. So let's put some units. These measurements are in centimetres, so we can drop those into there as well onto our chart just to make it all complete. So we can see here we don't really need our legend either, because we know what each observation is. So now we've formatted our scatter chart, and it's telling us correctly, so we've got everything labelled. Now, we can have a look quickly and analyse the trend between them, initially by calculating a line of best fit automatically, and Excel provides the trend line functionality to do that. We can see that when we select a trend line from our menu down here, we end up with this nice straight line that goes right through the middle of our data set. So and we can see that very closely follows the trend of our data. Now, this is really good for looking at the trends in the data, but the trend line functionality doesn't allow us to make calculations for values that we don't have. So for example, if we wanted to find the petal width for a flower with a petal length of 2.5, we don't have any readings in there, and the trend line doesn't really give us any functionality to calculate that. So in order to do this, we need to calculate our own regression model to do that. So we're going to start, we're going to move our chart out of the way for now. We'll come back to it later on. We're going to start by using the formula, by using our intercept and slope functions to populate our regression model. So here we have a set of values ranging from 1 through to 6.6 in ascending order, and they increment by 0.1 every time. So these are going to be the values for which we're going to calculate our regression model. So we're going to find the petal widths that correspond to these petal lengths based upon the observations that we have from this data. So recall from our lecture and from back at school that the formula for a straight line going through an x and a y plane is y equals mx plus b, where y is the y coordinate of our points, x is the x coordinate of our points, m is the slope of the line, and b is the y-intercept. So we can use this formula to calculate the value for any of our petal widths. So if we assume that our petal length is going to be our x value here, we can calculate our m and our b using our slope and y-intercept formulas and put this formula in to our spreadsheet to calculate our y value. So we start by calculating our y-intercept, and we do that by using the intercept function. So the intercept function, first of all, it asks for a set of known y values. Now, the values that appeared on our y-axis were our petal widths. So we drop those in, we click and drag all the way down to the bottom of the data set. You can see it's a little bit clunky to do this, but once we get to the bottom, we've completed that selection. We then go and put the known x values, which were the petal lengths, and we put them across the x-axis of our graph accordingly. So we'll select these values, moving all the way down through our spreadsheet here. And that's all that our formula asks for, so we finish up our formula, and you can see that we've calculated our y-intercept, and that's a negative number. That's fine, because all that means is that it's saying that this line of best fit will actually go right down here, and it'll hit the y-axis below the 0. So that's fine, we don't need to worry about that. The next thing we need to do is calculate the slope of our line of best fit. So that's going to dictate the angle that it rises at. And we do that using the slope formula. So we start again by selecting the known y values, which are our petal width. Once again, so we go down, we select all of our petal widths. We drag that down to the bottom here. And the next argument we need, next parameter we need for this one are our known y values. So these are our petal lengths because we had them on the y-axis of our model. So we drop those in, oops. And then that's all that formula asks for, so we finish up our function call. We can see we've got a slope of 0.4. Now that looks about right because the data goes up at almost a 45-degree angle, so a 45-degree angle would correspond to a slope of 0.5. So that seems quite feasible. So we've got all of the bits and pieces that we need for our formula now. So recall that our formula is going to be y equals mx plus b. Now the y values, we're going to store what's stored in this cell. So our x values are going to be our petal lengths because they appear on our x-axis. So if we start by putting our formula in, we're multiplying m, which is our slope, by x, which is our petal length, and we're adding the y-intercept, which is our b value stored over here, I13. So we can see that if we have a petal length of 1, the corresponding petal width will be 0.05. Now if we go down and have a look at our chart down here, we can see that this is where we start getting very low petal widths down here at value number 1. So that's perfectly feasible, looks correct. So let's start by trying to fill this down. Now you can see that it's starting to get a little bit strange here. The values aren't going to make much sense after a while. Now what's happening here is when we fill this down, we can see that it's updating the I values here. So all of a sudden when we fill to the next line down, we're no longer referencing the correct cells. So we need to go and put some absolute cell references in here so that we can fill our values down. So we do that by putting our dollar signs in front of the I, the row and the column values for our y-intercept and slope values. Now we should be able to fill this down without any problem. So you can see now we have feasible values for all of those numbers. So this data set is our regression model for our petal data. If we go through, we can plot this data and check to see if our regression model makes sense, to make sure we haven't made any problems. We do that by, again, plotting a scatter chart. You can see we've got a nice straight line that corresponds to the values that we've produced, that we have in our original data set. So it starts at about 1, 0, which is what we've got, and goes up to about 6, 2, 6 and 2, 5. So we've got our line of best fit, our regression model for our messy data set. And we can use this model, this formula, to calculate the value for any number. So if we want to know what the value is for 2.5, for example, we can go through and go and have a look in our regression model down here, and we can immediately see that at 2.5 we have a value of approximately 0.75 in there. So we've got a point very close to that. So our regression model has been able to successfully predict those values for which we have missing values, missing data. So that's just a nice little example of regression modeling in Excel. If you're in a science-based course, you'll probably be doing this with scientific data. If you're in an accounting or economics course, you might end up having to do this on economic side. So it's a very useful skill to have. So thanks for listening, guys.